All right, welcome to the video on solubility. What we're going to see here is another application of equilibrium. And previously what we learned about solubility was that things either dissolve or don't dissolve. Basically, if we put sodium chloride into solution, it'll completely dissolve, and we didn't really have much of a perspective on how much that would take or anything like that. But as it turns out, we've been learning about equilibrium, and we don't see that reactions just go from point A to point B like the sodium chloride dissolving in water would suggest. In reality, what we're going to have is some amount that's going to dissolve and some amount that won't. But because the solid is what's the reactant that's going to try to go into solution, we are going to approach equilibrium from just a slightly different and in some cases more simplified lens. But the idea is equilibrium is what's occurring here, and that solids really don't want to appear in those equilibrium expressions. This is a really relevant topic for all sorts of solution chemistry because even the insoluble compounds that we've learned actually do have their ions, anions and cations present in solution to a small degree, and what that degree is we'll be able to learn with understanding solubility equilibrium. All right, without much more, let's get into the video. Solubility picks up where we left off in Chem 1, where we learned general rules that salts were either soluble or insoluble. And this is still a really important distinction that we've used already in this video series too. Because if we see a salt that contains certain anions or cations, we can conclude that those are just going to be very soluble. So soluble that we can just consider them completely soluble, even though we'll see that at a limit, they will stop going into solution. And sodium chloride is a great example of this, that in practical amounts, it'll just keep going into solution. But in reality, if we were to distill all the water, like if you've tried to run a hot water bath that has salt in it or something like that in your chemistry lab, eventually the salt starts to precipitate out and form scale and things like that. And the ones that are always soluble follow this general rule. NCAA number 1 is a good way to remember them, where the N means nitrate, C is chlorate, A is acetate, and A is ammonium, plus, and probably the most important one, group 1 ions, group 1 metals like sodium or potassium. If they contain the ions on this list, then the ionic compound is always going to be soluble. So always good solubility if it follows NCAA number 1. However, this doesn't mean that every soluble compound is on this list. Some compounds are still soluble even though they don't adhere to this list, but it's a great starting point and one that you may be familiar with already. Additionally, when we talk about insoluble salts, they're actually a very small amount or a relatively small amount soluble as well. So this idea of solubility isn't actually this soluble versus insoluble idea that we've learned already, but it has a spectrum. And so, as we think about solubility in a more advanced sense here in Chemistry 2, what is solubility? And this is the amount that's going to go into solution, basically, and it's dependent on temperature. You've probably seen this already, where when you make something like iced tea or lemonade, it'll be easier to dissolve the sugar if it's warm. So at higher temperatures, the solubility of things is going to be greater. And so this is just to say that solubility is a temperature-dependent process, although we won't really get into that dependency here. It's expressed often in terms of molarity, so how many moles per liter of that salt can go into solution, but we can put it in any unit that we want that expresses a concentration, so grams per liter would work just as fine as well. When we say a solution is saturated, what does that mean? Well, that means that the maximum amount of solute has been dissolved. So consider a solution like a sponge. It has a certain amount for every solute that we can put into that solution. And after it is saturated, the remaining salt will remain in the solid phase. It will no longer go into solution and dissociate. And this is just like a sponge. A sponge can hold a certain amount of water until it is saturated, which means it doesn't hold any more, and the remaining water you would put on the sponge will just dribble away. What does it mean if a substance is insoluble? This means that it won't dissolve very much in that solvent. So while we saw this a lot in terms of double replacement reactions in Chem 1, where we bring two soluble compounds together to make an insoluble compound, that insoluble compound actually has a very small amount that is able to dissociate in solution. However, that amount is so small that it saturates the solution very quickly, and most of it comes out as a precipitate. So again, this is to say that even insoluble solids will dissolve a little bit, and we're going to study how this works in this chapter, and in doing so, we're going to look at a new equilibrium constant, a new capital K, to calculate the solubility. And this is the solubility product, and this is called KSP. And again, just like other Ks that we've looked at, it's just equilibrium applied to a specific reaction. And in this case, that reaction is the salt dissociating into solution, and the equilibrium that describes it is KSP. So how do we look at this for a certain reaction? This is silver phosphate that's dissociating into 3 silvers and 1 phosphate. And this picture below doesn't exactly match the silver phosphate example that's above. This shows a 1-to-1 compound below, but the idea is pretty similar, that we put it into solution, and while most of it is insoluble, it's still mostly the blocky conformation in the solid phase in the middle, some of the ions will dissociate and will go into solution. Once that solution is full of these ions, it won't accept any more. And so if we want to translate this into an equilibrium expression, we have the following, where it's silver plus cubed multiplied by phosphate just raised to the first power, the concentration of each of those. And if you look at this, you'll notice that this is exactly the same as products over reactants that we've been looking at the whole time, where we have this specific reaction. This is the solubility of silver phosphate, basically silver phosphate dissociating into its constituent ions, and the phosphate is solid, so it should not appear in the equilibrium expression, and we just therefore have the ions on the right side. And while this might look a little odd, this is the exact same thing, and this is something we should get comfortable with using. Now, one thing to remember is that KSP is still an equilibrium constant, which means that mathematically it's only going to hold if we are at equilibrium. And one good way to see that with solubility is if we have solid present, that means that we must be saturated, because if we didn't have solid present, that would mean that more could go into solution. Like if we put in a certain quantity of solid and it's going into solution and it disappears, that would suggest that there is more dissociation that could occur and we're not yet at equilibrium. Solubility and the saturation of a solution represents equilibrium. So if we are saturated, then KSP will hold. And again, because we generally do have a saturated solution with an insoluble salt that's remaining in solution, this will apply to perhaps more situations than we're used to with other equilibrium systems. Okay, so how do we calculate the solubility from KSP? Because it's very important to remember here that these are two distinct concepts, that KSP is a mathematical constant that helps us understand the solubility of this reaction a bit better. Whereas molar solubility, that's the actual number of moles that are going to dissolve per liter of solution, the molarity that we can potentially dissolve into a solution. So again, the KSP values and solubilities of solids can be very dramatically different, and the following is a good example of this. And just within this series, we see a range from 10 to the negative 14 to 10 to the negative 5. So a pretty big range for these different salts, which all are considered insoluble. The lower the value of KSP, the more reactant favored this is going to be, the less product favored. And for all of these KSP reactions, it's again the species dissociating. So KSP is going to apply to cadmium carbonate turning into cadmium and carbonate. And so all of these are having products being the ions that are going into solution, and therefore the smaller the value is, the less product favored and the less soluble it's going to be. If we have similar compounds, so if we have the same stoichiometry, which all of these are, this is to say 1 cation to 1 anion or 1 cation to 2 anions, if the similar compounds have the same stoichiometry, then what we'll see is that KSP is directly related to solubility. And we'll be able to conclude that if we have a more soluble compound, that it's going to have a higher KSP. However, does this always directly relate? Is this always true? And the answer is no, it's not quite true. And the reasoning is that if we have a 1-to-1 salt, we're going to have KSP be the mathematical product of A2 plus multiplied by B2 minus. It's going to be just 2 instances of ions that are coming out. However, if we have something like AB2, now we have two A2 pluses and two B minuses. So when we calculate KSP, we're actually multiplying 3 ion concentrations. And so this is the reason why KSP and the molar solubility are not the same, because KSP is a mathematical constant that's going to be fundamentally different based on the stoichiometry of this salt, whereas the solubility is what we're looking for generally. And the solubility is a physical quantity, which is how much can dissolve into a liter of solution. So the take home here is that if we have compounds with different stoichiometries, then we can't directly compare KSP to solubility, and we'll have to do a calculation. Okay, so how do we do these calculations? Let's take a look at the following. We say, what is the molar solubility of lead 2 chloride in water at a certain temperature if the KSP is a certain value? And so if you like, you can go ahead and pause the video here and give this one a try, but we've sort of just gotten started, so I'm going to work through it, but definitely pausing here to give it a try would be a good practice if you're up for it, and I'll show my answer in just a second. All right, as we're breaking down the solution, the very, very important thing to recognize is that KSP represents a reaction. It is the reaction that shows this lead 2 chloride dissociating in a solution. So what is that reaction? It's the following. And we're really looking at an ice table here where we're saying we have an unsaturated, just pure water solution that we're going to put this lead 2 chloride into. And so if we want to know the solubility, this is going to be the amount of lead 2 chloride that goes in a solution, so S. And let's envision this ice table that we're putting in the exact amount that is equal to the molar solubility of lead 2 chloride. So S is the amount of lead 2 chloride that goes in, and we start with no lead 2 and no chloride. The change that's going to occur is going to be S that dissociates, and as S amount of lead 2 chloride dissociates, it's going to form S amount of lead 2 and 2S of the chloride ion. And therefore at equilibrium we'll have a concentration of S for the lead 2 and 2S for the chloride. Now we take our KSP expression. This is at equilibrium, so we want to take that bottom row just like we have for other equilibrium reactions, and we say that it's the concentration of lead multiplied by the concentration of chloride squared because it's 2 chlorides. We put in our variables and we can solve for this single variable S, which gets us 0.016 molar. Now, it may look like we're double counting for the chlorides because we have 2S squared. It's like, where are we counting the 2? In the 2S or the squared? And this is where the idea that KSP is just a mathematical constant that's already taken this into account is so important. You need them both to be there because the squared, that's because there are 2 chlorides that need to come together. And the 2S, that's because there's twice as many of them. So even though it may look like double counting, it really is the way that we're supposed to do this, and is something to remember that when we have KSPs for different stoichiometries, they are going to be calculated on different orders of magnitude because we have a different, basically S raised to the power in the simplified form here is 3 because we have 3 ions this is dissociating into. The S that we calculate, this is the maximum amount of lead 2 chloride that's going to dissolve in water, and this is the molar solubility. So in other words, we use KSP to calculate S, the molar solubility, and if we know the KSP for a given ionic compound, we can calculate the solubility of that compound. The take home here is to say that 0.016 moles of lead chloride, lead 2 chloride, are going to dissolve in a liter of water, and when that occurs, the lead 2 and the chloride concentration are going to be 0.016 molar for the lead 2 because it's going to be equal to S, and it's going to be 0.032 molar for the chloride, 2S. And so this idea of the stoichiometry of these dissociating compounds is still very important because the chloride concentration will be twice as large as the lead 2 concentration. Okay, again, we cannot directly compare KSP and molar solubility if they don't have the same stoichiometry. So let's take a look at the following example. We have magnesium hydroxide and iron 2 carbonate. And the magnesium hydroxide, this is a 1:2 compound where we have 1 magnesium for 2 hydroxides. Whereas this lead 2 carbonate, the iron 2 carbonate, we have a 1:1 relationship. We have the KSPs, and we see that the iron compound has a larger KSP than the magnesium. However, the magnesium has a larger molar solubility than the iron. And this is because of the way that we calculate the solubility based off of KSP. Again, it depends on the stoichiometry of the salt, so direct comparison can only be made if they have the same stoichiometry. And if they don't, for example, if we weren't presented with the molar solubility here, and we were to say, just try to calculate that from KSP, we would say, well, they don't have the same stoichiometry, so even though the KSPs have a relationship, we can't conclude about the molar solubility until we run a quick calculation. As far as what that calculation is for the magnesium hydroxide, we say, well, it's magnesium hydroxide turning into magnesium and 2 hydroxides. Therefore, KSP is equal to magnesium times hydroxide squared. And from the same ice table breakdown that we did in the previous slide, we get the following. We can calculate KSP based on these molarities, and we end up with this value that's shown for KSP. If we want to check for the iron to carbonate, we notice that it's a 1-to-1 ratio, so this is the KSP expression. We know that it's going to be the solubility of each one is equal to the molar solubility, and we can put in the molar solubility, and we again recover KSP. So mathematically, this is what is the origins behind not being able to compare KSPs directly to molar solubility. And again, molar solubility is a physical quantity, and KSP is a mathematical constant that we use to calculate the molar solubility. Okay, so let's take a look at the following. AgCl, we have the KSP. We want to know if it's more or less soluble than lead-2 chloride. We found that the molar solubility of lead-2 chloride was 0.0162 molar. So what is the molar solubility of this silver chloride here? We have KSP. You want to start by making the reaction that silver chloride represents, and then solve for that molar solubility and compare to the lead-2 chloride solubility. So go ahead and pause the video here, see if you can make your way through this problem, and then we will discuss. All right, hopefully you've been able to make a good attempt at this problem. The first thing is you want to write the reaction. So silver chloride goes into silver plus and chloride. KSP represents a reaction. It's a solubility reaction, and it's the solubility of this species, and it has an equilibrium constant equal to what's shown here. We set up our ice table. Again, there's a lot of ways that you can put for the silver chloride column, but I think this idea that S is what's going into solution is the take-home, so I wouldn't stress too much about that column because, again, it's not really going to come into the expression either, so just presenting a couple different ways that I think make sense to me. Once we have this, we know the KSP is going to be the silver plus multiplied by the chloride, so we put in those S values, the unknown that we're calculating for, and we see that the solubility is equal to 1.3 times 10 to the negative 5. This is how much silver chloride is going to dissolve in a water solution that doesn't have any silver chloride in it at all. And what we conclude here is that this is smaller than the lead-2 chloride solubility, and therefore it's less soluble. It's quite a bit less soluble. It's about 1,000 times less soluble, and that's our answer here. So again, we really don't want to compare KSP values. We need to compare molar solubilities, but since that's our physical property, once we calculate that, we can compare those and conclude silver chloride is less soluble. Okay, for one last question here, let's look at the following. What is the silver plus concentration in solution if the chloride concentration is 0.01 molar? Note that this says in a solution containing silver chloride, so what does that mean exactly? And the KSP of silver chloride is provided as well. A couple of hints that are available to you. The first is you want to start with the reaction in KSP. And consider here, is this an ice table problem? Remember that the C represents change. So are we looking at a change in a reaction, or are we just investigating an equilibrium state? And if the solution contains solid silver chloride, what does this mean about equilibrium, saturation, and these other concepts that we've looked at already? So hopefully that's enough to get you started. Go ahead and pause the video here and see what you're able to come up with. All right, hopefully you've been able to make an attempt at this problem. The answer is we start with our KSP, so KSP is equal to silver times chloride. And we recognize here that this is a saturated solution, so it's at equilibrium. So we don't need to deal with any ice tables because we know that the solution is saturated. It contains the solid. And if it contains the solid, that means that it's not dissociating anymore, and the solution therefore is saturated and KSP is going to hold. Therefore, we simply plug in the value for chloride that we know that it's 0.01 molar, and we solve for silver plus. And what we get is that silver plus is equal to 1.8 times 10 to the negative 8 molar, and that's our answer. Now, In the previous slide, we calculated that the concentration of silver plus in pure water and the solubility of silver chloride is going to be 1.3 times 10 to the negative 5 molar. So what we find here in a solution that contains not even a lot of chloride, it's 1/100th of a molar, we see that there is 1,000-fold less solubility for the silver plus. And so this shows this common ion effect, we'll call it, where if there's an ion that comes from that salt already existing, well, it's kind of like some of the space in that solution is already occupied. So the solubility is going to be way less than if we have a pure water solution, if we have a solution that can accept as many ions as it possibly can. So hopefully this has gotten you started on these solubility problems. Remember, this is just another application of equilibrium, and when we say KSP, we're talking about a specific reaction. So if you're used to taking reactions, forming ice tables, and forming KSP expressions, or generally just K expressions, I think that you'll do pretty well in this chapter. All right, that's it for this video, and I look forward to discussing more chemistry in the next one.